Starting of the event also as a welcome session, so I'm very glad to welcome all of you, and more are about to come to this special program on image processing. So I realize it's the first week, almost the first day, and the plan to have a seminar emerged, roughly speaking, yesterday, and at some point in time we thought it would not be good to find a volunteer between yesterday and the afternoon and today out of this crowd here. So I raised my arm and volunteered myself, of course doing the worst thing. But okay, we'll see. But anyway, so I'm very happy to see so many people already now at the beginning of this program. I think all of you may know that we are running this program on variational methods in image processing here at the Newton Institute. So the official start date was the 29th, so yesterday, and will last until the 20th of December, with various activities in between. So we'll have a first workshop already next week. This is where I also said people are coming during these days and will stay on a little bit afterwards. Some of you will stay for the whole period. There will be another workshop roughly in the middle, and yet another workshop almost at the end of the program. The one in the middle will be, so the first one next week is more on fast solvers. The one in the middle is on learning aspects, and the one at the end is on shapes and flows, so covering different aspects, trying to combine the communities in image processing, imaging, computer vision, and neighboring topics. Mathematically, we talk about variational methods, optimization, partial differential equations, nonlinear ones, discretization, new aspects of learning, and abstract aspects like a shape space and related topics. Okay, I think I've said enough about the program. Certainly I should also mention it's not me who organizes this, it's Carola. She really did, I think it's fair to say, if I look at the other co-organizers here, that she really did a tremendous work in keeping us alert and on time with all the things which we needed to do. And then I just look through, so there is Ke Chen from Liverpool, he's co-organizing this program, Chu Cheng Tai, just behind co-organizing, Andrew Fitzgibbon, and I think yeah, this completes the group. Okay, so I chose a topic which perhaps at first glance looks familiar, but then somewhat strange, and then somewhat familiar again. So we have seen a lot of dualization in the recent years in optimization methods related to image processing. At some point we have identified that solving the dual problem, in particular if the primal problem is non-differentiable, might be a better point of view, because it may allow you to have different solvers and maybe quicker solvers even. Then it turns out, at least analytically, that there is a relation between, this is a reminder for myself not to be too slow, because there's a reception afterwards and we won't spoil that one for sure. So it turns out analytically there's an interesting aspect emerging in functional analysis, which is related to convex and dense embeddings of convex sets. Anticipating a little bit, if we talk about Sobolev spaces, well, we all think about RC infinity functions with or without boundary conditions densely embedded in one of those Sobolev spaces, and typically that's the case. The game changes completely if you take your favorite Sobolev space and put a convex constraint on it, like a bound constraint, as it might, for instance, occur in dual problems in image processing. Then density is not at all clear, and you might find simple counterexamples that density may fail. So this is why it's an interesting topic analytically when you talk about dualization or pre-dualization. I'll be a bit more specific about the pre in a second. As you may want to know how these problems which you're solving are connected to the problems which you really wanted to solve, the primal problem, which is the application image processing. So this is joint work. The dense embedding part is joint work with Carlos Rautenberg, Simon Rösel, who just graduated from Humboldt University, and the part on dualization and discretization is joint work with Julian Hahn, who is now in Austria working for a company called AVL, which also has a research component, and the various fundings which supported this research. Now let me start with the very familiar, perhaps even simple problem, the classical denoising problem in image processing. As we all know, you're given some data, little f here, in discrete terms. Let's assume it's a matrix, already having an image in mind. Let's, for simplicity, think it's square, but that's not the point here, obviously. And you would like to reconstruct an image out of this data. Data may be noisy, so you need to do some filtering, which after some prior discussion may be done by total variation, as you can see it here. So this is the little h indicates the mesh width. You may wonder, why am I talking about mesh width? Because if I take the discrete perspective, you may say one pixel is one away from the neighboring pixel in each direction, which is true in some sense, but wrong in some other sense, because it may give you some scaling of the problem, which if you take the same picture again and again under different refinement levels, you may learn that you need to suddenly adjust the regularization parameter properly, because you get a scaling because of not thinking in discretization width. For instance, if you would put your image on the unit square and then you would consider the pixels as being discrete points in the unit square, then you get a different mesh width, which would be roughly speaking 1 over the number of pixels plus 1, which would give you the proper scaling if you think about, for instance, quadrature rules. Okay, having said this, I won't touch on this for the rest of the talk, but let's assume now we would like to retrieve information from F, but filtering away noise by total variation, which I've done here in this specific way. And then there's always the compromise between data fidelity and filtering, and the compromise is controlled by the parameter alpha, which is supposed to be positive. And then, well, people have worked on this from many perspectives, starting from the infinite dimensional point of view, discretizing, finding artificial or pseudo time marching schemes for solving this, and recently it turned out that splitting methods might be also interesting, because they allow you in one way or another to bring in what we call now the Prox operator, which can be sometimes computed explicitly and can speed up certain steps of the procedure. Let's just try to look at such a splitting method from a primal point of view. What I'm doing here is I'm bringing in a new variable here, which is a vector valued quantity. So at every pixel I in the image, the p would be a vector. If you think about classical grayscale images, then this would be and in 2D, then this is a two-dimensional vector field, so to speak. And what I'm doing here is I introduce it instead of this gradient term, and penalize p from not being the gradient by the amount r, which is supposed to be positive penalty parameter. And this opens up an interesting perspective, because you may now decouple the problem into two steps. If you just allow me to go back, the first step could be fix p and solve for u. Second step, fix u and solve for p. And then you iterate these two steps until you're happy or waited long enough. Now, if we fix p, for instance, the problem which remains is this one here. Now, u is the unknown, p is fixed, and let's say fixed to some previous iterate. And you need to solve a problem which is very well understood. In partial differential terms, it would be an elliptic partial differential equation for which you have extremely fast solvers, like multigrid methods, for instance. So in that sense, the problem is easy. And I also would like to note that I use this symbol here, so the nabla with the dot, to identify with the negative sign here, to identify the dual of the gradient operator. So this is like the negative divergence, if you wish, speaking in terms of the divergence theorem. And of course, if you see this, be very careful. Sometimes people really discretize the Laplacian in that way. If you do this, then I would like you to go through the exercise and watch the boundary conditions. Typically, you get on one end of the story in 1D, for instance, the wrong boundary conditions. On the other end, you may get the right boundary conditions, but this has an adverse effect on the whole procedure. So this is just analytic way of writing it. But if you discretize, we talk about the 5-point Stansland specific way how we take in the boundary conditions. Never ever discretize the gradient, transpose the matrix, and multiply the other matrix by that object, because you always get the wrong boundary, almost always get the wrong boundary condition. Okay, now we have computed u given p, which means now we have to free p and fix u, and this is what we do in the second step. And if you go back to this problem, then you realize this is a simple operation going on here, and you can already compute everything explicitly and end up with this Prox operator here. So I don't write down the formula for the Prox operator. This should just inform you that this is a well understood problem, and you can find an explicit solution. So which means you really implement the function where you insert the p, the nabla u, and you get back a p without solving, really just evaluating. Okay, all is well defined, and it turns out that this alternating minimization converges for every fixed r, and as r goes to infinity, you get a solution of the denoising problem because you more penalize deviations from p being the gradient of u. Okay. So this is in finite dimensions, but typically the problem is posed in infinite dimensions. So whenever you open a paper on total variation-based denoising, then you see a version of what I have written down here. It's a variational problem. We are minimizing with respect to u over the functions of bounded variation over some image domain omega. This is my square. I have a quadratic data misfit, which is dictated typically by Gaussian type noise. Of course, it's not really Gaussian. What we mean is zero mean and a certain standard deviation from the zero. Just as a side note, because the realization of Gaussian noise is very rarely square integrable. Okay. And then we do filtering, and the filtering is done here by total variation, which I've written in this very strange sense, just to highlight the fact that the du is a measure-valued quantity, and usually this total variation seminorm is written down in this kind of dual fashion, where you look at the supremum over all s, which are C1 smooth, compactly supported in omega, and have an L infinity bound less equal 1. Okay, and then let's just repeat what we have done on the previous slide. Of course, you may ask why, because we have a functional algorithm already on the discrete problem, but as I told you, at some point in time, you may take your camera, you may change the resolution going from 1 megapixel to 5 megapixel, going to 10 megapixel, and this is what you may consider as different discretization levels of one and the same problem in image processing, which I've written down here. So it makes sense to understand whether your solver is stable under such resolution or mesh refinements, as we would call it in numerical analysis. Okay, so then let's think about the splitting method. I'm again introducing a new variable, but already now there is the question, in what sense should I understand the p? So this term here implies L1 regularity in the sense of Lebesgue regularity would be appropriate. And then the question is, in what space are we penalizing deviations of p from being the gradient? Let's assume we do it in L2. Then we end up with this problem, which is very reminiscent of this problem over here. Okay. One little thing, I can choose here, so this would be the finite dimensional vector norm at every pixel x, and you can choose whatever you like, because in finite dimensions all are equivalent. There are some aspects, of course. The L2 norm has the nice feature that the unit ball doesn't matter. So for the unit ball, it doesn't matter in which direction you're pointing. Whereas if you take, for instance, L1 or L infinity, you have directions where you have, let's say, the diagonals which can be longer, so to speak, and you're still in the unit ball. So there's a kind of anisotropy coming from the choice. But that's not the point. So you may think of the little L2 norm here as well. First mathematical question is, what would be a kind of minimum regularity function space where this problem is well posed? Well, first of all, let's think about the function space and then talk about the well posedness. Well, it seems that for for u, we have, what do we have? We have an L1 regularity, maybe L2 regularity, but that's fine by embedding. And we take one order, well, the L1 norm for the gradient. And for the p, obviously here we have the L1 norm, and so it seems that for the p we have the L1 vector norm, and then it dictates somehow the W11 regularity. So one observation is that would be a reasonable space for solving the problem, which then should be studied for Rn to infinity. And first observation is, as with the PV space, we are still in a non-reflexive setting, which is important if you think about the classical existence proof, where you compute infimizing sequences, think about boundedness and weakly convergent subsequences and things like this. Non-reflexivity has an implication there. On the other hand, you may say, but this is not correct, because I've just explained you that the du is not a nabla u. It's really has to be understood in the sense of a measure. So we think about a measure over omega with values in R2, so a vector valued measure, and that's what the p should really be. But then the appropriate setting here would be to not to take L2, but the measure norm here. But if we take the measure norm here, then it's just to ask the question, what's the gain? Because the problem seems to look as complicated as the problem up there if you think about fixing P and solving for U, because you still get the total variation semi-norm here. Okay. So first observation, we are non-reflexive. There is a departure from what we would expect, and this will have a consequence. Before I tell you a bit more about the consequences, a little guideline for the rest of the talk. I'll dwell for a while on the primal problem, soon realize this is not the place we should stay for a long time, move to the pre-dual problem, tell you about its advantages, but also about limitations of solvers, which would be backward solvers, or implicit, explicit solvers, talking in terminology of Lyons and Mercier. I'll give you some guideline on how to get over some shortcomings here, but without claiming that this is the method for the future. I just would like to highlight an issue and give you a way out, and from there you may design better solvers than the one which I present you here. I'll tell a little bit about discretization, because it's indeed an issue. If you talk about the primal and the dual problem, it turns out that by not doing proper discretization, you may get lots of numerical diffusion, even if your analysis is correct, and you don't get sharp interfaces or boundaries between regions. And finally, I come to the point which I started at the beginning with, which is how dualization or pre-dualization is connected to dense embeddings of convex sets, and how this influences the machinery here. And I'll be a bit more specific at the end. Okay, so let's get back to our problem. So if we say, okay, we don't want to have the same difficulties with the original problem, we stick to the L2 world, because that's when I differentiate, I get back a variant. Let me check. I have it later on, where I get back a variant with the elliptic problem for the U and the proximal operator for the P in a pointwise sense. But then, of course, the next step is to think about existence of a solution. And it turns out, while the original problem here has a solution, even a unique one, for that one there are no guarantees. And this has to do with the fact that you are jumping out of this environment of the total variation context. You work in a non-reflexive space, and there is no argument which would immediately guarantee that there exists a solution. On the other hand, it's quite obvious if you look at this objective here, it's non-negative. There is an infimum, so we can identify an infimizing sequence. So now we do so. We have an infimizing sequence U and Pn, and what we can claim for any zero sequence epsilon n, where each member of the sequence is strictly positive, you can always find an index, so to speak, that your inf is less than this, so that your current value of the objective is less or equal than the infimum plus some epsilon n. So you can trap, if you wait for long enough, your infimizing sequence in a certain bound between the infimum and this epsilon, in a sort of epsilon layer away from the infimum. So this is a straight application of the epsilon variational principle, but still we have no existence again. But the fact that we can conclude that this would hold true, we at least are able to do the following. So we say, well, we have in L2 some convergence, and we have on the P part a convergence to the total variation semi-norm as Rn goes to infinity. This is what n to infinity indicates here. And then we get back a solution of the original problem. So the picture is the following. We started with a problem which has a unique solution. We wanted to do splitting, but in a way that each sub-step remains simple, which means if I differentiate with respect to u, solve an elliptic equation. If you fix u and differentiate with respect to p, I would like to apply the prox operator. So this is what dictates this format here. So then I have no solution. I have an epsilon optimal solution, so to speak, but as Rn goes to infinity, all is fine. I get back a solution of the original problem. Okay, so that's an interesting observation. In one way, I would say, okay, you're inconsistent when you do this splitting, as we've seen it initially, but in the limiting process, if you take Rn to infinity, all will be fine. But there's a fine tuning between mesh width going to 0 and n going to infinity. Okay, and as I said earlier, if we would do a proper formulation where we have a guaranteed minimizer, well, then we would need to consider P as a vector measure, and then we end up with this total variation measure again, and that problem, if you think about it, for a fixed P is as expensive as the total variation problem. So in that sense, the splitting algorithm would not be fast, because a sub-problem would be as expensive as the original problem, and you won't gain. Okay. So you may say, yes, sure, but we do augmented Lagrangians and not direct splitting. Okay, so what could be an augmented Lagrangian approach? You consider a new constraint. Again, I'm bringing the P in the very same way as before, but I consider now a constraint. The constraint would be nabla U has to be equal P. Of course, we can debate about the nabla here, but let's be generous for the second. This is a constraint, and an augmented Lagrangian formally applied says, I write down the Lagrangian, assuming that the multiplier would exist. So you see the objective function plus the term which comes from the constraint, and this penalization comes from the augmentation principle in the augmented Lagrangian context. So what you see here is now an augmented Lagrangian version, where the entire hope would be, by tuning the sequence lambda n, which would be the Lagrangian multiplier to this equality constraint, you can get out some good properties. Well, number one is, you may ask yourself, why are people so keen on using the augmented Lagrangian? Because we know that non-smooth penalty functions are typically exact, meaning if the penalty parameter is large enough, a solution of the original problem will solve the penalized problem. And typically smooth penalty functions are not exact, which means you have to drive your parameter always to infinity. Now, augmented Lagrangians have the strength that while being differentiable, they can still be exact penalty functions, if you have a right choice of the Lagrangian multiplier. Okay, so the caveat is you need to have information on the multiplier, and if you have the right multiplier here, then the remaining part is exact. But here is where the trouble partially comes already, because if you want to keep lambda n simple, like for instance in L2 as indicated here, then it turns out not to be the right space for the optimization problem. It's not the right space for the optimization problem, so it's not an exact penalty function. In finite dimensions, you wouldn't see this. If you write this down in Rn, it's of course an exact penalty function. But in function space, the trouble is I need to worry what would be the appropriate function space environment for the Lagrangian multiplier, because if you don't fit the environment, you can't get exactness of the penalty function. And otherwise, the same issues concern, I don't go through the same issues remain as in the previous example. I'm not going to the details here. So again, splitting is not possible. Okay, so what are the intermediate conclusions? In Rn, all is fine. The discrete algorithm is most like the resolution dependent, which means as you refine your resolution of your image over the same image domain, your solver will get more expensive. Not just because every iteration gets more expensive, but it may also need more iterations as you refine. If you don't believe me, I'll be here until December. You just try it out with your favorite splitting method, and if you find out otherwise, I'll be very happy to know, and I'll throw away the slide. And if not, you may still come, because maybe there's a lesson to learn in addition here. Okay, but if we do some what I call here proper split or splitting objectives, then it seems that the remaining problems are as expensive to solve as the original problem. Again, if I want to be faithful to the function space context in the sense of discretizing an infinite dimensional problem. And again, augmented Lagrangians are no longer exact penalty functions in general, otherwise the same issues also remain as for the splitting. So let's abandon the primal problem for the time being and consider a pre-dual formulation. Now, I'm sure that there are many experts in the room, so I would not need to show a slide on the dualization framework, but let me just quickly recall it anyway, just to be on the same page. Let's assume we have two Banach spaces, which are called here capital V and Y, with topological duals indicated by star here. And let's assume we have a linear operator, which is also continuous from V to Y, and two convex functions, curly f and curly g, which are also assumed to be proper and lower semi-continuous. We also assume that there exists a point V0 in the Banach space V, such that both f at V0 and g at lambda V0 are finite, and the g is continuous at lambda V0. If you don't want to memorize this, of course you shouldn't, you just look into convex calculus rules and you will identify that this is what's needed if you want to apply the chain rule, for instance, and have a certain format for the chain rule, which would be if you differentiate g with respect to v naught, you would like to see lambda star subdifferential g at lambda v. In order to get this representation, you need certain regularity conditions, and those are the regularity conditions. So they look like constraint qualifications in a sense. Under these conditions, you may solve the primal problem, or you may solve a dual problem, which involves here the convex conjugate functions, and they will both have the same objective value. I just wrote down the convex conjugate, which relates to the slope of a primal function. For instance, the convex conjugate of an affine function is a constant. The convex conjugate of a quadratic function is a quadratic because the convex conjugates tell you how the slopes change as the base point changes. And you have a relation between the primal solution, which I call here V bar, and the dual solution, which I call here Q bar. And if you want to read more about this, then you go back to the book Bekeland Temam. I just enrolled in the library today, and I even saw the book because I had 10 minutes of walking around on the second floor. So if you don't believe me, just look it up. And with this faithful duality framework, you can do the following. You look at the problem, which looks like this. So you're minimizing the divergence of S, a vector field, plus our image data F over L2, subject to a constraint, which is a pointwise almost everywhere constraint. Pointwise is clear, almost everywhere means up to a set of measure 0 in the sense of Lebesgue. And alpha is indeed our regularization parameter. Now this problem is well posed in HDiff. What is HDiff? It's the space of L2 vector fields which have a divergence in L2, and if I add a little 0 here, I mean also that I have homogeneous Dirichlet boundary conditions here in the sense of the normal on the boundary. So nu is the unit normal to the boundary of omega. So if you think about this in an image domain, which could be square, then you capture only one component of your vector field on the boundary respectively. Okay, so this is what this boundary condition tells you. But that's proper. And with this, equipped with this space, and of course now considering the divergence as a linear continuous operator from H0 diff to L2, which we can do on this space, this admits a solution. Question, will the solution be unique? Answer, in general not, because the divergence has a non-trivial kernel, and it would be a miracle if all elements of the non-trivial kernel would be filtered out by the constraints. Some will be, but not all of them. So there is a solution, but it's not unique. But from an image processing point of view, we don't care, because all that matters is the primal quantity u bar, which is the image, and it turns out that the divergence is unique. So the divergence of S is unique, which can be seen from the problem here with a little bit of experience. And this suffices to have a unique reconstruction. And we don't care whether S is unique or not. You may care a little bit if you apply some of your favorite algorithms which operate on the dual, because those may never converge on the dual. Some do, some not. So be careful whatever solver you design, there might be a consequence of the fact that you don't have uniqueness here. Okay, now, but we want to do splitting. Now if we do splitting, again, idea would be, well, first question is, where is the troublemaker here? Because this seems simple, differentiable and quadratic. The troublemaker could be the constraint here, which I include here through an indicator function. So R is the set which identifies the constraint, and I add the indicator function, which is 0 if the vector field satisfies the constraint, and which is plus infinity otherwise. And what I do now, instead of plugging in the S here, I plug in a new variable t and penalize t from being S, from not being S, by quantity Qn, and Qn is positive, and again Qn may go to infinity. And this allows me again to look at the problem first of all in H0 diff and across L2, but in an alternating fashion. I may fix t, solve for S, and I may fix S and solve for t. So I have two steps. And again, the sub-problems. The first step, fixing t and solving for S, is well understood. It's not as nice as we have seen before, because this is really the gradient of the divergence operator. This is something which you see in elasticity theory. So this is an elliptic, but not strongly elliptic path. So it's a trouble in a sense, but it's fixed by the fact that we multiply a multiple of the identity here. Okay, and there's a right-hand side. So you can solve this again by multigrid, but I think Kev would tell you that this is a bit more delicate, perhaps depending on the Q, because of that operator here. It's not so convenient like the negative Laplacian. On the other hand, if you fix then S once you solve it from here and compute T, well then things get simple because this is just a projection. So this is minimizing the quadratic given S subject to this indicator. So it's really projection onto R. The L2 projection. The L2 projection is kind to us because we can do it in a pointwise fashion. If, for instance, at every point, this is the little L2 norm, it's like projecting onto a ball, which can be done immediately. Okay. Now, what do we know about convergence of solutions? Well, we do have solutions S and Tn. This is, in a sense, already better posed the problem compared to the primal. As Qn goes to infinity, we indeed get the solution of what I call here the pre-dual. Well, have I ever told you why I call it the pre-dual? Not yet. I call it the pre-dual because obviously the dual of this problem is the primal problem, and I can't get back the image. Okay, so I call it the pre-dual because starting from here, dualizing according to Ekelund-Temam, I get this first order condition which relates the dual variable S bar to the primal variable U bar, which is indeed the image I would like to compute. Okay, so what I can say here analytically is as Qn goes to infinity, I get the sequence of solutions of the pre-dual which converges to the primal solution, even in a very interesting sense that the divergence is converged to the divergence of S bar, something we don't see very often. But what we don't know is whether the alternating minimization method converges. I'm just saying if I were able to solve the problem, I generate the sequence and those solutions converge. But the alternating minimization is a method to solve for every S, N, and T, and so now we need to know whether we can indeed compute S, N, and T by alternating minimization. For that, let's have a look at the theory à la Lyons, Mercier, Goldstein, and many others which have worked on this after that. Let me give you a bit more general picture of that theory, and then we fit it into our context. A and B and A plus B are assumed to be maximal monotone operators. And C is assumed to be a bounded linear operator, all on a Hilbert space H. And the abstract problem we are interested in is a problem, it's a root finding problem, where we are looking for an S in our Hilbert space H such that 0 is an element of A plus BS. So A and B can as well be set-valued maps. So I was not confining myself to single-valued operators here. They could be set-valued. For instance, there could be subdifferentials. And given an initial guess as 0, we have variants of algorithms for doing so. So there is a backward algorithm or implicit method, because you really need to solve. Implicit always means there has to be an effort, like in time-dependent problems. With implicit discretization, you really have to make an effort to get to the next iterate by solving a problem. So you first solve the problem with the resolvent I plus lambda B, and then you solve it with I plus lambda A, and in between there might be C. Very often we see C being equal to the identity. There's also a forward, backward, or implicit version where you first just evaluate. So this is more convenient. So this is like evaluating the operator at SK, applying C if you have it, and then solving another problem. So this is the expensive part, and this is typically the cheaper part. So these are two versions which you may consider. And then, what do we know about convergence? Now, strong convergence is obtained by assuming that B is coercive, and strong linear convergence is implied by B considered Lipschitz continuous and strongly monotone. So there's a very nice thesis by a PhD student of Rockefeller's who summarized many of those results related to the splitting algorithms. And although you may also get weak convergence under weaker conditions than those which are indicated up here, a convergence to 0 is only guaranteed under very specific circumstances. If we look at the forward-backward problem, we get again strong convergence under Lipschitz continuity of B, with either A or B being strongly monotone and further assumptions on our parameter lambda. Okay, so that's what we have, and now the point is, can we fit our image processing problem? Remember, this would be our problem here. Obviously, we are solving problems here. It looks like a backward scheme. Would it fit into one of those, and can we inherit convergence immediately? Now, what are our choices of function spaces there are in essence only two, either H diff or L2. Okay? But it turns out that in either scenario, A and or B would not satisfy the conditions for convergence. So the splitting methods don't converge for such problems. For instance, I just exemplarically focus on the backward scheme where H would be the H0 diff operator. If I consider A being the derivative which I get with respect to S, this would be the A. Remember there was I plus lambda A, and A would be that derivative here. You see the gradient divergence, which is a well understood operator, but as I indicated, it's not coercive. The L2 part is missing. We just capture one. So if you think about the weak forms, you get divergence of F and you can get another divergence of S, but you don't get the L2 part of the H0 diff norm, so you don't get coercivity. Again, in finite dimensions, don't worry, it will work. But in infinite dimensions, there's an issue, which you will feel as you refine your resolution. Now, what about the projection? So this would be the second part here. So this, as you can see, the B part would be the subdifferential of the indicator function, which can be well computed. This is a normal cone mapping in L2. So which means we have maximal monotonicity in L2, but not in H, so not in H0 diff. Okay, so which means, and further B neither Lipschitz over H nor coercive, so which means we don't get convergence for this scheme. Now you can say, okay, we may get weak convergence, which is indeed true, but not guaranteed to 0 of A plus B, which is not nice. Now if you consider a different scheme where we don't consider the L2 but something else, which would be the intersection with H0 diff, then we would need to project in H0 diff, obviously, because this is part of our R set now. So R before was in L2, and this is what made the projection simple. You could do it in a pointwise fashion. Something else I would ask you to pay attention whether people are faithful to the function space context, because you can't do a pointwise projection if you have a differential operator sitting in here. For this, you really need to solve a more expensive problem. So this is not a projection. This is the norm in H0 diff, and you need to minimize this over R tilde, which is still the same convex constraint set. Let me just go back, which is still the same set here, but a different space, and that matters. Okay, so which means projection is expensive. So the second part is solving a variational inequality with a differential operator, so nothing pointwise. Okay, so that's the conclusion for the time being. So you have some convergence results which are not really satisfactory, and what we usually like to see are stronger types of convergence which we won't get with these forward-backward schemes. Now a little reminiscence of the remedy for this would be the following. You do the same as you have seen it before in the H0 diff and the projection in the L2 fashion, but you sneak in a little parameter eta here, which is between 0 and 1. So the original problem, remember the original splitting which caused the trouble, so we couldn't get, for instance, coercivity because of the L2 projection only here, would have eta equal 1. As soon as I insert here eta between 0 and 1, things are fine. So I will not go to the details here, but now you have a parameter-dependent solution S eta and a consequence in T as well because of the S eta sitting in here. But at least projection is still simple, can be done in a pointwise fashion, and this problem is as expensive as the one which we have seen before, which I claim to be not as easy as the negative Laplacian, but still easy to solve. So this is fine. And for that you can get some theories saying, well, the method converges, number one, and as eta converges to 1, you get back a solution of the original problem. So for as soon as you select eta less than 1, you can apply Banach's fixed point theorem, you get convergence for the scheme in the underlying function spaces, and as eta goes to 1, you get back a solution of the original problem. So in that sense is consistent, and the problem really solves the and the limit S star and its projection really solves the pre-dual problem. And if you think this would not be sharp, we did some numerical experiments indicating, I think it's maybe too much for this talk here, but indicating that Lipschitz properties indeed go wrong as eta goes closer to 1. So as eta is smaller than 1, everything is Lipschitz. If it gets closer to 1, it's no longer. So it seems that what we claim here is somewhat sharp, at least. So this is what this first graph will show you. As you go to 1, it gets steeper and steeper, so you have no Lipschitz behavior expected here. Now, so this concludes my section on primal dual pre-dualization. Let's quickly talk about discretization. Well, it turns out, let me just move forward and then go back. Let's assume you have an image, a very simple image, and you do a discretization. Again, if you don't believe me, you take your forward difference operator, you do whatever you want to do for the divergence. For instance, look up what you see in the Bock-Jean-Paul paper, for instance, and then you solve the problem and you look at the result and you will see numerical diffusion. Okay, you will see numerical diffusion. Whereas if you do a staggered grid scheme, what you see here is I'm reconstructing, it's a simple image just for test purposes, I'm reconstructing and the grayscales are mapped onto a random color code in order to highlight diffusion clearly, because from these grayscales it's very hard to say whether there is a diffusion here or not. But if you have a random color code here, you can quickly see whether something goes wrong or not. And you can see that there's a very sharp interface between one part and the other part, okay, indicating that the discretization matters a lot. I should have shown you some of the other pictures which I don't have here, but if you're more interested, I have test runs with other discretizations where you can really see numerical diffusion along the interface. And to keep this story short, what you need to do for the dual variable, the S quantity, is a staggered grid, which is not amazing from a, let's say, computational fluid dynamics point of view, where people look at incompressibility conditions, and they have, if you use, for instance, finite difference discretizations, which people barely do, I understand, then you would use staggered grids for the vector fields in order to get an inf sup property for convergence. And what you see here is different discretization nodes. You have, let's say, the pixels in black, and then you have new nodes, neighboring nodes in this direction, neighboring nodes in that direction, and your vector fields will be discretized. Typically, let's say that would be the x direction for the S1 for the first component of the S vector field, and you would discretize it here and there, and the S2 component would be discretized here and there, and that's what you do, and this would be the discretization point for your image UI. Okay, and then, well, you can generate these meshes, and based on this message, you look at meshes. You look at the specific discretization. These are backward differences on the two component vector fields S1 and S2. The minus indicates backward differences on this mesh with respect to the first component and the second component. You see forward differences for the gradient operator on the corresponding meshes, and then we have this projection in there, which is a bit delicate. I think I won't go to the details here, but remember, we have to project. But now we don't have we have to project the vector field. So there was this P of R. But now how do I project if the first component lives on these two nodes and the second component lives on these two nodes? So it's not that they all would live on one node. So I can't do a simple projection. So I have to combine different pieces of information in this projection. And this is what these operators do. Depending on where you sit with your discretization, you have either take these averages or other averages, and that's how the projection is done. Okay, so that's an issue then on the staggered grid, but this can be resolved, and otherwise you just solve these equations and we do the projection as I have just explained it and get back such a result. And here we did the Pepper image. Here it's not about getting the best reconstruction, it's about how the interfaces are resolved. And you can again see from this sketch here, this would be the noisy image, and this is the reconstruction. Again, noisy image in color coding, so this is in random color coding, this is why it looks so awful here. Of course, I mean, you see this information in the grayscale context. But here you can see, again in the random color coding, how this looks like, and you can see very little random colors around the interfaces, which means there's very little numerical diffusion coming from that scheme. I mean, of course, I realize this is not the best possible reconstruction. Again, this is not the point of this test. The test is to see whether there is random colors next to the interfaces, because that would indicate that the discretization introduces numerical diffusion. And if you have numerical diffusion, you should find a scheme to avoid this as much as possible. This is an intermediate conclusion. So the primal problem was problematic. We couldn't get function space methods going. The pre-dual was much better, but we found out that backward, forward, backward iterations are still complicated because we don't get convergence theory right away from what we know. And there seems also little hope to do otherwise. But once you introduce this parameter, you get convergence. And again, let me emphasize, I'm not claiming that this is the method everybody should use. It's just highlighting where the issues are buried and what should be done as a remedy. And finally, once you use primal dual problems, very carefully think about discretizing the primal and discretizing the dual. Please don't just discretize the primal and take transposes and believe you have a good discretization for the dual. This is not the case. And the staggered grid in this context was a good discretization, at least for our purposes. Let me finish off by quickly getting to this pre-dual problem. I was very short on this. At some point I said, have I ever told you that this is even the pre-dual of the image processing problem? And I said it is. But there is a very subtle point in there, because remember, we had this HDiff space with the convex constraint that the vector field has to be in a pointwise almost everywhere fashion less or equal alpha. So this is a convex set in some function space, Banach space, and we would like to understand, if you think about how the PV seminorm was defined, there were the C1 functions with compact support, whether such functions would be densely embedded, if those would be constrained in a pointwise fashion in the HDiff set with the same pointwise constraint. So for that purpose, I get back to more general more general optimization problem, minimizing f of u over some Banach space X with the convex non-empty constraint set K, and closed of course as well. First order condition can be a variational inequality as the one which I've written down here, where this A would then be one part of the F and the J could be a second part of the F. A similar situation would arise, for instance, for the image processing problem, where the J would be the non-smooth part and the A would be the quadratic misfit part, for instance. But you may consider the variational inequality as an independent problem in its own right. Okay, so very often for efficient solutions we need to understand perturbation. What is a perturbation? It could be data perturbation, it could be some stability under whatever approximations, but one approximation which is also interesting is, for instance, discretization. You may consider discretization a very special perturbation, and for that we need to understand what's going on. And important tools, just in case you would like to get more into the details, which I won't have time to, is gamma convergence or Moscow convergence. We talk about infinite dimensional semi-smooth Newton methods, and we have seen fractal duality earlier. And again, the underlying paradigm is we would like to understand the infinite dimensional problem structure, which seems to be crucial for both the perturbed version but also for the understanding of the design of algorithms as we've seen it. Now, what's the general form of the density question? So I gave you an example. So H0 diff vector fields pointwise almost everywhere less equal alpha is one set, and the other set would be C1 vector fields pointwise constrained by alpha. Is this latter set densely embedded in the first set? If that's the case, then dualization works. In a very general way, you may formulate it as follows. Let's assume we have two Banach spaces y and x, where the closure of y equals x. And the question now would be, if we intersect K with Y and close it with respect to the X norm, is this the set K, which would be the K set related to the X space? Okay, and I've given you a couple of relevances already, analytical, algorithmic one, and in applications we have, for instance, the image restoration, but many more, elastoplasticity, Bingham flows, and so on. Okay, maybe I don't go through the quasi-monotone application, but rather, because there are many examples, but rather go to some embedding results. Let's see where they are. Okay. Yeah, this is Galerkin methods. Okay, so let's consider what I have just discussed. In our little example, G was the identity. In the general context, we also did it for G, which not identity, like could be the gradient, could be the divergence, but in our example we talked about identity. X was our H0 diff space. Alpha here could be alpha of x, which could be now a spatially varying regularization, but in our example alpha was just a constant function, the regularization parameter. Then this would be the dual constraint set. X is H0 diff, this is identity, this is a constant, okay? And now we ask the question which I've shown you on the previous slide. If we look at K intersected with smooth functions, and we close it with respect to the X norm, do we get back that set? And okay, here it's written down anyway again. If you just do simple, because you may think about the proof technique, if you do simple modification, the trouble is you will violate constraints, because modification always has a kind of local support, and if you have a certain constraint less equal alpha and you do modification, then you might violate the constraint. So you can't use certain modification and cutoff arguments. So the results which we get for continuous obstacles, and obviously the constant is a perfect example for this, the regularity of the obstacle plays a role for this embedding question in general, which I won't go into, but if somebody's interested, I'm more than happy to talk about this offline later on. So we get all these embeddings here. So if you, for instance, think about X of omega being either an LP space, a Sobolev space of once generalized differentiable functions which have gradient and functions in LP with homogeneous diagonal boundary conditions, or you're in H0 diff, you get such an embedding that the C infinity functions in dimension D, in our imaging example would be dimension 2, closed with respect to any of those norms, gives you back the constraint set in the underlying space here. Okay, so this is indeed a density result. And that's what you use, and I don't talk about this one in the image processing context. Let's remember our primal problem. I put a more complicated version here even. Remember we had K being identity so far. I can take K being a linear continuous operator from L2 to L2, otherwise the same meaning. I can even allow alpha being a function. Before we had it in front of the integral, indicating alpha is just a scalar, but it could be a function in general. So that the pre-dual problem, which looks very similar to what we had before, there was the L2 norm, which is now slightly different because of the K operator. If K is L identity, then you just get L2 here. We had the same problem, but there was no alpha X, there was just alpha. And I told you that the dual of this one is that problem, which is indeed true because of this dense embedding result, actually. And that's where, for instance, you need it. And if you don't believe it, you may find example where this goes wrong. And if you think it's not relevant, then I ask you to look through the literature. And again, I'll be here until December. And you can, I would be interesting to see how many papers you can find where this aspect has been generously overlooked, and I'm sure that you'll come with a pile of those to my desk. With this, I would like to close here. I think I've told you the story about the first part. The second part should just remind us, whenever we do dualization, this dense embedding is not always for free, but is very much needed when we look about constraints, which very naturally occur when the primal problem has a norm, because as soon as you have a non-differentiability, and the typical ones we have are norms or max-type differentiabilities, you get the pointwise constraint for the dual, and then you should remember the dense embedding results, because only then the connection between the dual and the primal is really firm and rigorous. With this, I think I have used up my time, and thank you very much for your attention. But certainly I'm happy to answer questions in the room here if you have some, and some other questions, but still mathematical ones, of course, afterwards in the social event. Other questions? Yes?
You mentioned that for the Lagrangian use L1, and then there will be as typical as the original problem. But that's for this problem. For more general problems that use L1 penalization, and you can get simpler algorithms. So the question that, do you know anyone who proved convergence for general Lagrangian with L1 penalization?
Okay, let me just go back just to understand. Here.
Yeah.
You mean this one?
Yeah. No, not this one. The penalization is L1.
No.
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 For all I know.
You had some more somewhere.
Yeah, this one.
This one. No,
Right.
for this one, I don't know. No.
You see, anyone, you see that normally penalization is
But-
doing L2 square.
Yeah.
So if you don't use L2, like you use LP, so even P equal to 1,
Yeah,
P equal to infinity, if you know anyone who did convergence analysis.
But the point is the problem gets more complicated.
For this one, yes. But for other problems, it's getting simpler. You see, even for your second one, so we go, all right.
I mean, for this problem here. No, I mean, so the point is, for this problem, I'm not aware that people have looked at the augmented Lagrangian because there's not really a gain by using the augmented Lagrangian, but I agree that the augmented Lagrangian has been used as a general principle very successfully for problems in infinite dimensional space. About L1, I would need to think. I mean, I think you did quite some work on this, and I see examples where it works reasonably well. The only thing I wanted to highlight here is that for this specific example, I see in the literature that people try to use augmented Lagrangian as a way out and claim by choosing lambda well it works, and I would say this is certainly true, but this is a finite dimensional observation on a corresponding grid. But of course there could be other problem instances where you don't have this difficulty. I fully agree, because here's the second trouble, which is if I want to keep this simple in L2 and lambda here in L2, then again there's a mismatch in regularities which spoils the exact penalization property, which of course you will have in other problems. So I'm not stating here that augmented Lagrangians are not good tools in infinite dimensional spaces. It's quite the opposite. So there are successful applications. It's just sometimes one has to be careful. It might not be a resolution consistent remedy for some of the problems which other methods go through. Yes. Okay, I think Eve was first, and then.
Because I just had a follow-up on this.
Okay.
Very briefly,
Yeah.
but so what I find interesting, if I understood you correctly, is connected to this point that the results you get in function space might explain what happens in finite dimensions, that the convergence is not scale independent.
Yes.
And because you're closer and closer to the infinite dimensional problem, which is at some point not well closer.
Yeah.
And so, does this also maybe suggest something the other way around of how you might change the finite dimensional problem such that you get better scaling?
I think so.
Yeah.
It does, but I don't have a very quick answer on the spot here. I think you really need to do a careful scaling of things and of norms. If you can replace your L2 norm by a norm which in the limit is consistent with something which we see here, which perhaps is doable, I mean, Søren Bartels has worked a little bit along this direction recently, then you learn something from that. So I mean, you can of course have a finite dimensional approach which is you start from finite dimensions and you're completely consistent with infinite dimensions. That's what multigrid, for instance, does. And I think there's a lesson to learn here as well. You need to rescale your norms that you converge into the right environment, which is not if you just do the classical quadrature rule for L2. That's a good question, actually. Yeah. Yeah.
Like a quick question. The one is on the slide that you presented with the Lagrangian and the R term, just the previous slide, not this one. Why in the second formulation you need the term with the Rn over 2? Why do you need this term since you have the constraint already? That P equal gradient of U.
Yeah, but let's say this is an analog of the classical augmented Lagrangian. So whenever you have an equality constraint, then you would see some term which penalizes constraint violations. So this would be a penalization of the equality constraint. In that sense, I mean, the norm is perhaps not the right one, I agree, but just using the Lagrangian might not give you a well-posed problem.
And in this case, you do not need to run Rn to infinity.
In general, well, with the consistent augmented Lagrangian and a good choice of lambda not, but in this context it would need to go to infinity. Yeah.
The other question
Yeah.
maybe answer those. The eta that you introduced.
Yes.
Can you see it in as a kind of acceleration parameter?
Oh. Acceleration, internally I feel it's the opposite,
Okay.
but because it just allows you to get contraction. So it's a little bit like forcing contraction to apply Banach's fixed point theorem for this iteration in the wanted spaces where every step is still simple. So we've seen that from the Lyons-Mercier-Goldstein type theory, you would need to either go to an expensive projection or do something else. And here I may keep things as simple as I wanted them to be, but I need to somehow introduce a parameter. So now what I have a sequence of parameterized solutions, and I typically would do some homotopy with respect to eta to go to 1, which can be done and it works. Yeah. Okay. Eve?
Yeah, my question was also about the eta. First,
Yeah.
does it have some equivalent in the primal domain if you take it back, or?
It's a good question. For sure it will have. I haven't looked at it. I can't quickly anticipate what it would be. Yeah, but a good question. Yeah.
I mean, again, related. If you restate it, multiply eta into t, so now it's like your projection onto delta r
Yeah.
is 1 over eta. You're making the box 1 over eta bigger.
Yeah.
I don't think that's visible in the primal. Obviously, you get a different algorithm if you take eta out of the step 2 and put it into step 3.
Yeah. So okay, I need to think now. Okay, we see it down here. So we have. So this is the most compact form. I mean, here the point is I need to understand you. So you're saying you can absorb it here.
Yeah, if you
But-
absorb it there, then it appears. in 3.
Okay, and then you have to correct for it here.
Yeah.
And then you get, of course, a different projection. Okay, I agree, but I'm now not quick enough to see what I do to the primal problem by doing these 2 steps.
Nor am I.
Yeah, because it's not just simply changing the regularization parameter, which would be it does something more. It changes the format of the regularization term. I don't think by awful lot. Very often we see, for instance, if I stabilize the dual by some norm, okay, maybe, as we speak about this, okay, now the constraint is missing. If there would be the constraint, at least one thing I could say, if let's assume there is a constraint, and you add, ignore this term for the time being, and you add this term here, then you smooth the primal problem a little bit around the kink. And the reason is, now here by this you make the S unique, because now you have the divergence part, and here you have the L2 part. So you have coercivity, and so you get the unique S. Without that term, you don't get the unique S, and this is where you sit in the non-differentiability, which is the kink of the of the norm in the primal. So, in a sense, this has an influence on this type of smoothing the eta here, and there is a little shift as well. So maybe we're shifting a little bit. So I would anticipate that there is. No, but I take it back. No, I can't fully see what it does to the primal. I'll work it out. It's a good question, certainly. Yeah.
In your first splitting model,
Yeah.
the one, the
This
red thing.
Yeah. Yeah.
Yes. This P, the divergence part is you don't need that, I think. If you do a hot decomposition, they will realize one part is not needed because the P can be decomposed as the curl-free and the divergence-free part. They are orthogonal to each other, more or less.
Mm-hmm.
So the divergence part is coercive. It will vanish if you take the minimization just for that part. Then you end up with a gradient of something minus gradient of u plus the gradient of that thing. So that might be the model, essential model for this.
Yeah. If you mean
If you do
for P,
composition,
yeah.
then you see the essential part is the gradient.
This
of
is
something.
this is a
This is the infinite dimensional version of cosmos.
Yeah.
In the
I-
finite D, you might not.
I agree. So that's simpler, I agree, but what's the consequence for the problem in P then? Because the charming thing with this formulation was that one would need to work it out is that the fact that here you have then this simple prox type operator where you plug in the nabla U. But if the P is now replaced by the nabla of the other component, so to speak, then this gets more complicated. So there is a price to pay, but I agree there are other ways of looking at this problem. So the only thing I
There are
did
more variables.
yeah. So there's a price to pay. So, but I agree, you can use Hodge decomposition and learn from the structure and come up with a different formulation. It's just very often we see that people penalize in the L2 sense from this P minus nabla U.
It's roughly equivalent.
Yeah, but that's also a good point. Yeah. Mhm. Further questions, comments, disappointments, expressions of happiness. Nothing like this. Okay, I see some people smiling at least at the end of a talk. I think this is a good sign. Thank you very much for your attention here. I think we'll have a little social event going on afterwards, and maybe Carola has some more announcements. I'm not sure. No? Okay, just, it just looked like. Okay, thank you again. Thank you very much.